All right, so this lecture is going to go over 2D motion, kind of introduction concepts here that we need for to analyze motion in 2 dimensions. And so we're starting here with the Pythagorean theorem. I'll try not to talk too much about it, but we'll see how it goes. So when we deal with the Pythagorean theorem, we're dealing with right triangles. So I'm going to go ahead and draw one right here. And okay, something like that, right? And then this angle right here, which we represent with this square or this box, that is a 90-degree angle. And so that's how we denote that. The side, right, the side that is across from 90 is the hypotenuse. And you always want to spot this when you're doing SOH. So the hypotenuse is the side across from the 90-degree angle. So there can be other triangles that don't have 90-degree angles. As long as their 3 angles add up to 180, I think it's good. But yeah, so this idea of the Pythagorean theorem applies to right triangles specifically, and they show up quite a bit. Write the Pythagorean theorem, so we just write it as a squared plus b squared equals c squared. Where students sometimes have trouble is that they remember that, but they don't forget they forget the fact that c has to be alone. So c is always the hypotenuse, and that's the idea. So when you write the Pythagorean theorem, though, c always gets to be alone on its own side because it's the largest side of the right triangle. So that's worth writing down, that the hypotenuse is always the longest side of a right triangle. Okay, so I know I didn't explain what the Pythagorean theorem means in words, but that's okay. I wrote this note guide a long time ago. It is far from perfect, and I'm just using it to talk about these ideas. And the most important thing is that you understand them, and this is a refresher because this is stuff I would hope you've already learned in math class, and so, but we're going over it just to make sure. All right, so a couple examples here. I'm just going to set these up. I may or may not solve them, but to show you how this works, a squared, always write your formula out. This is the best way to memorize them. We can see here that 18 is going to be A, 8 is going to be B, and X is going to be C. And so over here I can then write, doesn't matter, A or B, 18 or 8, doesn't matter. I'm going to go with 18 as A. All right. So units here, it's actually interesting to write, so I'm going to write the units because the units get squared too. And then instead of C, we're going to use X. We could just keep it as C. It doesn't really matter, but I'm going to do that. What is 18 squared? I don't know 18 squared. Dang. I know a lot of my, I know 12 squared and 13 squared. But I don't know 18 squared, and I would like to think I have a calculator right here. I probably could have just figured it out in my head just as quick, but that's okay. 18 times 18 is 324. Okay. So let's go ahead and solve this. Notice the meters get squared too. All right, we add those two together. What's that, 88? Yeah, I think that's 388. And we'll just go ahead and square root both sides. So that will allow us to get the answer here. And so the square root of 388, let's see, is equal to 19.70. Whoops. Okay, let's see if... And notice the meters get squared, or the square meters get square rooted, so we're left with meters. And this is equal to x. Okay, this next one I'm not going to do, but I am going to set up. And this is one of the ones that I'd said kind of be careful of. And I'm going to go ahead and write it down here because we're not going to do number 6. This is one where you have to make sure that x is either a or b, and that 23 is c. Right? Well, kind of like before, but yeah, I think you just have to be careful for that. So here we're going to have a squared plus b squared equals c squared. We'll then have x squared plus 6 squared is equal to 23 squared. Once again, I'll write the units because it's kind of neat. Okay, so and I'm not going to do that one, but I can guarantee for a fact, just like we said earlier, that x is going to be less than 23. And that's a good check at the end to make sure you're doing it right. If we look back up here at this last one, c is our hypotenuse, and therefore it has to be longer than either 8 or 18 or 8. And so is it? Yes, it is. It's 19.7. So that's just a good mental check to make sure that you're doing it right. Or if you made a dumb mistake, and then that way you can catch those, right? Because you know that the hypotenuse has to be the longest side. All right, that's all there really is to it. So nothing hopefully new for you there. Let's take a look at this. So I'm going to kind of go out of order with some of these pages because I think I'm going to come back to that page and start down here, I want to say, with number 3, with just defining SOH. I think I'm going to do it like this. Once again, I'm not really following this note guide to a T. So what SOH is it's an acronym, right? It's something that stands for something. And it is a bit of a mnemonic device, meaning like it is useful in helping you remember 3 formulas. So let's look at what those formulas are. They are as follows. SOH, what that stands for is the sine of theta. You always have to take the sine of something. There has to be an angle there, and that angle is going to be theta. And I'll mention that in a second here again, is equal to the opposite over the hypotenuse. All right. How do we make sense of this? We should probably draw a picture of a triangle and label those sides. So I'm actually going to draw 2 triangles because something interesting kind of happens here with 2 triangles. So there we have one, and here we have a second one that looks very similar. All right. So I'm going to have 2 triangles here. Let's go ahead and make this angle right here equal to theta. And we'll say that that is 30 degrees. We'll then do another example where this angle right here is theta, and it's equal to 60 degrees. All right. Okay. So let's go ahead and put a little color in there so you know what angle I'm talking about. That's what I'm talking about. All right, good. So then let's go ahead and put a 90-degree angle right there and there. I'll go ahead and make those. Well, I don't. You know where it is because it's a square. All right, so so whenever you get a right triangle, you're always going to label three things, and this is super important whenever you do SOH, is that you always label your triangle correctly. So what we have here is pretty much identical triangles, right? Because their angles have to add up to 180. So, but theta is a different angle in both of them, and theta is just a Greek letter. I'll just write that right over here, what theta is. Theta is this symbol right here. And I think upper and lowercase theta are like that. Like one is just larger and one is smaller, but whatever. Okay, we're not too worried about that. So with these, why theta? You know, why not some other angle? I don't know. You could use another angle. You can use phi, right? You could use alpha. You could use beta. What does beta look like? I think that's beta right there. That's one of it's either uppercase or lowercase beta, or you could use gamma. What is gamma? I think. God, why has this been so long since I've used gamma? I feel like it looks like alpha. I feel like that's wrong. God, I don't know. I can't think of it off the top of my head. I was actually just going to turn it this way, but I can't draw. Jeez. Let's see. Oh well. We're not going to worry about it right this second. It's beside the point. Okay, so coming back to this, I could have picked any Greek letter, right? That's kind of what I'm trying to get at. All right, but for some reason in math classes, math teachers like using theta, so I like using theta, but I could use phi or phi, I could use epsilon, could use omega, yeah, you know, mu, there's a ton to choose from. All right, so coming back to this, when we label our right triangles, always start with across from 90 being the hip. Super easy to find, super easy to label, right? Here's 90 degrees in red right here. And so the hip is always across from it, always the longest side. The next one I always like to pick out is the opposite. Opposite is always across from theta. And what I wanted to show you, maybe these are identical triangles, like legit identical triangles, right? Like everything is the same about them. And so I'm saying that this side is 5, this side is 13, and this is 12, right? I'm pretty sure 5, 12, 13 is a thing, from geometry class. It's been a while. But there's 3, 4, 5 right triangles. I could have just stick to that. I think 5, 12, 13 is another one. But I don't know. I'm gonna go with it and say that it's right. Okay, so we have 5, 12, 13 right here, and my point is this, right? That in one of these drawings, because theta is the 30-degree angle in the top one, then the 5 is the opposite. So we always label the opposite as being opposite theta, across from theta, right? Just like I'm going to draw a couple of vectors here. So I'm saying across from 90 is the hypotenuse, right? And I can do the same thing with, oh, geez, Louise, how the heck, what? All right, okay, saved by the undo button. I finally found that undo button. All right, geez, I just can't erase that. I don't know what the deal is. Maybe it's because my eraser's so big. All right, let me try it. All right, there we go. All right, that's better. All right, and then the same way we can say across from theta, right? Here's theta. Across from this side is always opposite. And that's so important, and so you really can't screw that up. So what I'm trying to say here, you have to, before you even mess with SOH, which a lot of students like to just get the fraction out and start working the problem. That's wrong. Really label. Start by labeling. Label your hip, label your opposite, and the side that's left has to be the adjacent. Let me go ahead and label that. So the 12 is the adjacent here. And that's kind of how it goes, right? But what does adjacent mean? It means next to, so next to theta. So what we're saying here then is for opposite, it means across from theta. Notice it's all about theta, right? It's relative to theta. And for adjacent, and we mean next to theta. And so that's kind of the key idea. Because of that logic, right, that the opposite and the adjacent are all about theta, then looking down at the bottom triangle, we can see now that 12 in the bottom triangle has to be what? Well, it's across from theta, which is the orange angle, so it has to be the opposite. All right, so this is where it's tricky, right? So the same identical triangles, similar, identical, whatever the word is, they're exactly the same. They can have opposite, or they can have different opposites and adjacents based on what you call theta. Theta will never be the 90-degree angle. It has to be one of the other two angles. But do you call it, is the orange angle theta? Is it the 60? Is the green angle theta? It's the 30? And that changes your opposite and your adjacent. So what's adjacent to 60? You might say the hypotenuse is next to 60. Yeah, but it's the hypotenuse, so it can't be the adjacent too. So you got to go ahead and call the 5 the adjacent. All right, so there you go. There you have it. So that's super important. Label your triangles correctly before you use SOH. Okay, so SOH. How to use it, right? What do we do here? So with SOH, what we have is a way to memorize 3 formulas. And what you can see with the first one that I drew here is that SOH, right? Let me grab yellow. All right, SOH comes from the fact that it's telling you this order right here. That when you write this formula, it's always sine theta equals opposite over hypotenuse. All right, by that same logic then, let me go ahead and get a green marker. All right, CAH is telling me a different formula, and that's going to be that cosine of theta is equal to the adjacent over the hypotenuse. And you can see CAH, the same exact order. So SOH is not just something cool to remember, it's something cool to remember to help you remember other cool things. And so let's do the last one, TOA. So this is going to be TOA, and TOA is tangent theta is equal to the opposite over the adjacent. All right, so let me go ahead and show you that TOA in the same exact order. And that's it. So your 2 steps here doing SOH problems are 1, label the sides correctly. The sides are labeled relative to theta. And so once you know where theta is, you can label your adjacent and your opposite. The hypotenuse doesn't change regardless of theta because it's always across from 90. And the second thing is that you memorize this crazy word, SOH, or mnemonic or acronym. Acronym is where each letter stands for something. Mnemonic device is just something that helps you remember. And these things work, right? They are useful. Anyways, so you have SOH as that, and each letter stands for one of these, or each set of 3 letters stands for one of these formulas, and they help you memorize these 3 formulas. I guess if you just knew the 3 formulas, you wouldn't have to memorize or know SOH, right? You'd already have it memorized, but I don't know. It's just a little easier this way. Okay, good. So let's go ahead now then, and we're going to save resolving vectors into components, and we'll now go back to this second page here, which says, it gives us a few things to talk about here with the angle, definition of tangent. I actually want to, for us to go We don't usually do a lot of tan problems for whatever reason in my class, and should we do one? I guess. What the heck, right? All right, so let me just go ahead and do a tan problem for you right here. So I'm going to label the right angle, which is right here. And so once we've done that, go ahead and label your three sides. See if you can do it. Take about 10 seconds there, label your three sides. Also label theta. All right, you should have said across from 90 is your hip. You should have said across from theta. You're going to be your 49.8. So this is theta. This angle right here is across from that is your opposite. And next to theta is your adjacent, which is x. So here, I labeled the hypotenuse, even though I don't really care about it, right? It's not going to come into play in this problem. It's not going to matter, but I still label it regardless. So label your three sides, and then move forward from there. So then I decide what formula do I need, and all I do is look at what I know. So meaning I look at the fact that I have, let me pick a different color here. All right, I have a opposite that I know something about, I have an adjacent that I know something about, and I have a theta that I know something about. So then I grab the right formula, which in this case I already told you what it's going to be. It's going to be TOA because we have an opposite and an adjacent, and we have a theta that we know something about. So this is going to be the best one to use here is TOA. So let's go ahead and go back to this. I like to write the formula out because that way we work on memorizing these. So tan theta is equal to the opposite over the adjacent. All right, let's go ahead and plug in our values. I think we know the value for theta is 49.8 degrees. Your calculator does have to be in degrees. A lot of times you might have it in radians. Radians are awesome. We use them in physics class sometimes, but most of the time when we're in this, especially in this chapter of 2D motion, we're gonna have our calculator in degrees. This may be a problem if you're in pre-calc, because I know in pre-calc they like to use radians quite a bit. And I can talk about radians someday and explain those because they're kind of neat too. 136 meters is going to be my opposite, and x is going to be my adjacent. All right, I really like this problem because the variable is on the bottom, which a lot of times kids struggle with. So let's get that variable off the bottom, and then let's get it alone. So let's go ahead and get it off the bottom. We'll multiply both sides by x. Cancel, cancel. We can go ahead and rewrite, right? It's x tan 49.8 is equal to 136 meters. And then we have to get x alone, right? So we have x just over here, but it's next to this tan 49.8. So I'm going to go ahead and divide by tan 49.8. All right, so we end up canceling these, and we get x is equal to 136 meters over tan 49.8. We really don't worry about the degrees sign, right? It's not technically a unit we're too concerned with. It's kind of like a shadow unit. It's there when we want it to be there, and then it kind of just goes away when we don't need it anymore. So we have 136. I'm just going to type it into my calculator, divided by, yeah, I'm in degrees. Okay, I said a check. 49.8. I'm getting 114.93. Whoops. And that's going to be, that's going to be units of meters. I don't know what I hit there. Okay. So this is going to be our value for our adjacent. We can't really check this one all too easily. I guess we could say because this other angle up here, which we don't know what it is, right? Well, we do know it's the complement of 49.8, so it's 40.2, right? So this 40.2 degree angle, which I'll color in orange up here, is going to be across from a shorter side than the larger angle. The 49.8 is going to be across from a larger side. I guess that's a kind of a way to check it. That's kind of checking out and making sense. But yeah, I don't know. I think we're kind of stuck with it unless we do another TOA problem, and I really don't want to do that. So good. Let me add a page really quick here. Let's see. I'll talk about radians really quick, and just because I did mention them. There is a formula. It goes something like this here. It is theta times r is equal to s. And what it says is that if you have a circle and you have a, let's say, let's draw a line to the center of the circle, and you have another line right here, that you have an angle which is theta. And we'll go ahead and make that in radians, right? I don't know what it is, and just whatever. It's in radians, okay? And you have a radius, which we'll call r here. Let me get rid of this. It doesn't have to be here. Right? And I guess technically both of these lines are r, right? Okay, but I'm not going to worry about that right now. I'll just stick with one of them. And we have this arc length hanging out here. And we're going to call this S. Okay, so why this is important? Because radians are cool, even though we like degrees, or I like degrees, right? 360 degrees once around the circle, super easy. The reason why radians are also cool is, or even maybe even better than degrees, is because of this relationship that you can take this angle, this yellow angle in radians, right? Whatever theta radians is, and multiply it by the radius and get this purple line here and get the arc length. That is very cool. So you can take any angle, multiply it by the radius, and get the arc length. All right, that's what this says, right? So where r is the radius and s is the arc length. And so you might be like, all right, well, whatever, right? All right, well, here's an example of this in action right here, right? Let's say we have another circle. Yes, all right. And then, and we have another center of the circle, right? And let's draw R again. I should probably make R a different color, but that's okay. I won't worry about it. All right, and then we're going to go all the way around the circle with S. What would that angle be in radians? So this is going to be S in blue. What would that angle be all the way around the circle? Say 360 degrees, but we're in radians, right? So what angle is this right here? You should be saying 2 pi radians. How do you know? How are you expected to know that? I think this is one of those things you got to remember. So 2 pi rad is the same as 360 degrees. Okay, so you go all the way around the circle, which is 2 pi radians. let's look at that. So we're saying here that your theta in radians is 2 pi rad. You're going to multiply this by the radius, and you're going to get the distance all the way around the circle, which has another name other than s. What would that be? Well, let's look at the other side. 2 pi times the radius. That should look familiar because that is the formula for the distance all the way around the circle, which is the circumference. All right, so now you can understand that this formula right here that you've used in math class probably quite a few times, the circumference equals 2 pi r. You might also say, well, 2 times the radius is actually the diameter, so it's the same as pi times diameter. Okay, right? And I'm not sure what symbol they use for diameter, if it's just little d or maybe big D, but pi times the diameter is the same thing. All right, whatever. You can see that this formula, circumference equals 2 pi times the radius, comes from this relationship right here, that the arc length is equal to the angle in radians times the radius. All right, so this is why radians are cool. You can't do that with degrees. You can't just take your degrees 360 and multiply by the radius and get the distance around the circle. No. And that's why the SI unit in science is actually radians and not degrees. Even though I like degrees better, it doesn't matter. This relationship is just so neat that's why radians wins out. Okay. But that being said, we're going to stick to degrees in this chapter. And so make sure if you're in a math class that uses radians, you watch out and watch that, because I've had many kids in physics classes who forget to flip their calculator over and then take a test and just get every problem wrong, and they're like, what? And then it turns out it's because of their calculator. All right, so what else do we guys say? All right, so really what I want to do is this next example. Let me add in one more page here, and then we're going to be done, because I think we will have covered mostly what I want to talk about. So let's add in a page. All right. This is an interesting problem, because now we have a little bit about this right triangle, but we don't have the same things, right? And so let me show you what we got here. So across from 90 is the hip. Once again, we don't know the hip. I'm going to stick with blue right in here, just because I like when that stands out from the note guide itself. All right, so across from that 90-degree angle is the hip. Here's theta down here. Across from that is going to be the opposite. And then next to the yellow angle, the side that's left, is the adjacent. All right, so what we have here is the question not of what's the hypotenuse, but we now have a question that we didn't consider before, and we can't do with just SOH alone. And that is, what is this angle here, right? What is theta? So what we need to do then is take a look at the formula we would think we could use, right? Which, if we have an opposite, we have an adjacent, we have an angle. Let's check which formula to use. Op, adjacent, and angle, op, adjacent, and angle. Well, this one is op, hip, and an angle, so that's not going to work. This one is adjacent, hip, and an angle. We don't know hip, so that's not going to work. And it's going to be this one again, right? Op, adjacent, and an angle. Okay, so let's go ahead and go back to, where were we? Right here. Okay, so let's go back to this, and let's write that tan formula. I think I have room right here, but if not, I have the extra sheet of paper. And before we plug numbers in, let's look at this. We want to solve for theta, but we got this tan function that's going to be a problem. So we have to undo tan. There is, in order to do that, we have to take the inverse tan function of tan theta. So we have to hit like an undo button to get rid of tan. So what I'm saying here is tan theta will eat tan. So we're going to go ahead and tan or I'm sorry, tan inverse will eat tan theta. So what I'm saying here is then that we're gonna tan inverse both sides like this. Let me write this. So we're taking tan inverse of tan theta, and that's going to equal the tan inverse of op over adjacent. So by doing that, like I said, tan inverse eats tan, and they're gone, and you're left with, it's like an undo button, the inverse function. And so we're left with theta then over here is equal to tan inverse of op over adjacent. And there are tan inverse buttons on your calculator. Now you have to be careful with the -1 exponent in math class, because sometimes it means tan inverse as meaning an undo, and sometimes it means 1 over tan, or the reciprocal. So you have to be careful, and there's not a clear way of distinguishing that with tan to the -1. So whether it's the inverse, right, the undo button, or the reciprocal, which is 1 over the tan, so you have to just be careful with that. So anyways, coming back to this, we now have a new formula, right, that we can apply to this problem to solve for theta. So let's go ahead and do that. We got those numbers up above. I'm just going to bring them down here. We can say then theta is equal to tan inverse of the opposite, which is 4.87 meters, over the adjacent of 15 meters. If you're ever doing a problem where you have negative signs and your op and your adjacent, disregard those, because you don't want those in your tan inverse function. Something else you can notice here is the units you don't have to worry about, because check it out, right? They both cancel away. So we're taking the tan inverse of 4.87 divided by 15. I'm going to go ahead and plug this in the calculator. Once again, this tan inverse has a button on your calculator on your phone, just like tan has a button. All right, so I'm getting theta, I'm getting theta is equal to 17.99 degrees. Once again, we're always in degrees in this chapter. All right, so roughly 18 degrees. And that's how it's done. So a new function there in tan inverse maybe for some of you, and that's why we're going to use it sometimes in this class, is because maybe we have an x and a y velocity, and they're acting like a right triangle, and we want to find the angle between them, or not between them, that's 90, but the angle in that triangle. All right, so that's it. I'll probably leave you some practice to do, but I'll post that on Schoology what the practice is, if there is some practice. And yeah, so I guess we'll stop there. Have a good day.